Good afternoon, everyone, and welcome to today's webinar on HVAC design with CFD, particularly designing for EN 15251 compliance. My name is David. I'm one of the co-founders and CEO of SimScale. Background in CFD, so that might be helpful today. And I'll be giving this short presentation. It's going to be just around 20 minutes, not more today. Let's get some technical aspect out of the way. The GoToWebinar application allows you to ask questions. So at any point during this webinar today, just type in the question in this field, and by the end of it, I'm going to go through the list. Typically, it's way too many questions to answer in this session, but I'll try my best. And if not, we have a very active forum. My contact information is in the information of this webinar, so you can just reach out to me afterwards in case I haven't covered your question. Furthermore, we are recording this webinar, and it's going to be put on YouTube afterwards. So in case you want to send this to a colleague or review it later, that's not a problem. We're going to send the recording, I guess, by tonight, maybe tomorrow morning, to everyone. All right, that being said, I would suggest we directly dig into it. A few things, or a few words before we go into the technical details of designing for EN 15251. We have lots of customers that care about thermal comfort and that design HVAC systems, and I'm all the time amazed by how they do it, right? Because it is tough. And the reason why it's tough is that there's two sort of fundamental mechanisms that compete with each other, right? Or objectives that compete with each other. On the one hand, you can see on the left that there's a rising awareness for the fact that thermal comfort is important, right? More and more standards cover it in lots of standards and codes. It's already in there, and so we want to design for thermal comfort, but taking into account that the temperature, the outside temperature varies over time, etc., and throughout the year, you want to control the thermal environment inside your building, right? And control means typically you need to put energy in, right? Because a passively ventilated or a passively conditioned environment is most of the time not as responsive as an actively ventilated environment. So to design for thermal comfort means typically you want to control ventilation. So you want to mechanically ventilate and condition the air. Opposed to that is the other trend that more and more buildings and more standards ensure or require the building to be energy efficient. So energy efficiency is a big topic among all our customers in the AEC sector. So while they want to ventilate a space to ensure thermal comfort, they also want to make this very energy efficient, right? And these opposing objectives or partially opposing objectives are what makes this so tough, right? And the reason why we're seeing so many customers being successful with CFD is because flow simulation allows them to iterate early in the design process to validate that a particular design actually is the right balance between being energy efficient while making sure that later, while the building is operating, I can run my air conditioning system at the operating point that I was predicting and not more. And, all of this makes sense. That's where CFD comes in as a handy tool for a design engineer in this field. In these short webinars, we typically want to really show a practical application, right? We just don't want to do the theory. It's not going to be a tutorial how to exactly do it. It's really just a design scenario that's very similar to what we see many customers doing. And the design scenario we're going to look at today is such a theater. And the scenario in this case is we're looking at a new theater, right? So it's not a renovation, it's a new theater we're building. But even if it would be a renovation, under the standard or the code EN 15251, this would typically fall under a category 2 building, right? And I'm sure most of the audience is familiar with that code, but the quick background to this is that the category sort of says the requirements to the thermal comfort, right? Category 1 would be something like hospitals, clean rooms, etc. Category 3 is something, older buildings where you cannot put the requirements so high. Category 2 is everything that's new or freshly renovated. And so we're now tasked as an engineer here to design the HVAC system. So where do we bring in air? Where do we bring it out? How do we make sure that, that the temperature is acceptable in here? And we're obviously mechanically constrained where we are able to put the HVAC outlets and inlets, these sorts of things. So a typical scenario we see customers faced with. What we're doing in here, just to look in a more detail at the design, we're looking at this and are saying, okay, based on our experience and based on how we would, typically without simulation design the system would be, okay, we're using a mixed ventilation system. So we're bringing in air from the top over the occupants here. Obviously the occupants here on the right, let me quickly bring my drawing tools. Okay, so we have, we're bringing it at the top and we're using a mixing ventilation system. So we're bringing it in here, and we have then our air will move down, will condition our occupant zone here, but obviously those guys produce heat, so we have metabolic heat sources for all humans. Down here we bring the air out. Here are the out registers where we bring out the air from the occupant beneath the seats here, right? And then we have a couple of additional outlets over here. That's sort of the rough setup of this case. And now, since we are particularly interested in designing for this code, what we are, the two metrics that are important for this code are PMV and PPD. And both of these metrics, and I'm sure people in the thermal comfort sector or people in the HVAC design sector know these metrics, both help us quantify the level of thermal comfort, right? How occupants will perceive the environment in this building. And both of them are different measures and very similar to each other. Predicted mean vote essentially takes into account velocity and temperature information in there. And we account for the metabolic rate and the clothing coefficient, or the clothing insulation. And metabolic rate would be something like if we're designing for a sports center, recreation center where people move and do sports, right, we would have a higher metabolic rate. In our scenario, we're looking at a theater, so people sit and watch the theater going on. So it is typically a 1.0 metabolic rate coefficient. Clothing coefficient, same here. If it's summer, we would go with something like 0.5. If it's winter, we'll go with something like 0.2. We're going to see later what we'll assume. That's the predicted mean vote, and it's a measure that ranges from -3 to +3, and we're shooting for 0. We're going to see that in a second. Derived from PMV is PPD, predicted percentage of dissatisfied, and that's a measure of how many occupants or how many people would perceive the environment of not satisfactory, right? It uses it's very similar to PMV. It has this similar input parameters. It doesn't look at additional physics than PMV, and it's also just a positive measure, right? Since it's a percentage. And both of these metrics are being used in the code we're designing for today. And so the big question is, in order for our design here to be compliant with EN 15251, we need to be able to bring PMV in a range between -0.5 to +0.5. And same goes for PPD. We're shooting for predicted percentage of dissatisfied to be below 10%, right? And that's what CFD now comes down to, right? Because it's tough. I mean, obviously there's hand calculations, there's tables, there's graphs that I can use to sort of, better understand the impact of my design. And there's obviously very experienced engineers that have seen many things. So there's other things I can turn to that help me get a good design that meets these requirements. But ultimately, the stories of buildings where ultimately the air conditioning system was not able to deliver on a specific operating point the desired thermal comfort are endless, right? There's so many large occupant spaces that are not well, that are either don't meet the thermal comfort that was intended to be there, or they don't meet it based on the energy efficiency the engineer had foreseen for it, right? And the ability, now CFD comes in as a tool that gives us the ability to simply validate whether or not our air conditioning system brings the thermal comfort we want it to bring, right? And that just based on the technical drawings, just based on our CAD data. And that's the beauty of CFD, right? And how it helps in designing for thermal comfort. And that's what we're going to do now in the next 10 minutes. Before we do that, let's take a look at why SimScale, right? There's a ton of CFD tools out there. CFD has been around since decades, and you can get from all different software vendors software for that. So why did we develop another tool? And the reason is simple. We wanted CFD and simulation in general to be accessible. This means we do not want our customers to, invest a ton in hardware, have high performance computing hardware standing around that's aging, that gets old, that somebody needs to maintain, these sorts of things. That's why we built it as an web application. You're going to see later, everything we do, all the simulations we ran were simply done from a web browser. Second piece to this is we wanted it to be cost efficient, meaning with all the upfront investment in hardware gone, we also wanted to get all the upfront investment in software to be gone, right? So SimScale comes as a web application with a pay-as-you-go model. You can start it for free on a community plan. And if you want to do professional work, it starts with a low fixed minimum investment, and you just pay for the computing time and the computing power you need. Last but not least, simulation is traditionally something's done by PhDs, by people that have a specific education or that have been specifically trained on a particular simulation type. And we wanted it to be easier to use. We wanted it to be accessible to everyone. And for that, we've not just built it to be a tool, but also to be a community and a platform for collaboration between our support team and our customers, between our customers and their clients, etc. Since it is in the cloud, everybody participating in SimScale and everybody with a SimScale account can collaborate with others in real time on the same data. And that allows for a different way how support can be done, these sorts of things. We're going to see later that in action. To get a feeling for the workflow, I'm gonna show you the application in a second, also in directly as a as a short live demo. But to get a feeling for the workflow, here on the left you can see the CAD model, right? So the start for every simulation in SimScale is always the CAD model. We are compatible with several CAD software systems, with all of them via general exchange data formats such as STEP or IGES, with some specific ones such as, for example, SolidWorks, Rhino, Onshape. You can bring in the models directly, also Autodesk Inventor, and we're adding formats as we go. And so from there, the next step is always you set up the physics. So here we can see a finite volume mesh being generated, and then you set up the boundary conditions, sort of here's my air coming in, here's my air going out, this is the temperature, these sorts of things. And then last but not least, once your simulation has been carried out, you can visualize the physical quantities you've been computing. In this case, we're mainly interested in velocity and temperature across my CAD model. Thermal comfort is one of the applications that can be done in SimScale, but in fact, at the back end of SimScale, we have a multi-physics suite of solvers. So we're also running structural mechanics analysis, classical incompressible flow simulations, but also multi-phase flow simulations, etc. So it's a whole range of physics that's possible in SimScale. Today, we are mainly focused at internal flow simulations, right? So low temperature, low velocity, non-isothermal flows. That's what we're looking at today. But our customers in the AEC sector are doing all sorts of things. So here you can see at the top right, that's a simulation looking at wind comfort of pedestrians. So a wind going through a city structure. Here in the lower right, you can see a contaminant control simulation of carbon monoxide in a parking lot. So we're seeing many different applications from the architecture world being simulated on SimScale. All right, enough talking. Let's have a look at the application itself. And for that, I'll quickly bring over a browser window. Here you can see this is a standard Google Chrome, right? I'm running on a standard Windows computer, could be Linux, could be something else, you name it. And if you don't have an account yet, you can create an account here in the top right, where now here it says dHeine. In my case, I'm already logged in, and so I can jump simply to the dashboard where I can see my latest simulation projects. And if I open one of these projects up, I'm inside the SimScale application. And this is the theater we've been looking at, if you remember correctly. Let's look at design 1, because we said what we're mainly interested in is, what we're initially simulating is a setup in which we're bringing in the air as in a mixing ventilation, with a mixing ventilation strategy from the top. Let's quickly hide this guy. And there you go, right? So we can see this is now, all of this is 3D interaction that happens on my local graphics card, right? It's using WebGL. So I brought in my CAD model and I can interact with the scene. I can look at these guys. Okay, I can see that I simplified the humans a bit. You can see that we have the outlets down here, right? So, I mean, standard CAD model. I think the interesting thing here is just it's in a web browser, right? Everything runs in a web browser. Okay, and then the next step is I generate a mesh for it and set up the physics. So let's quickly jump over here and take a look at this setup, right? So this is now my simulation setup that you can see here on the left. So it starts with me choosing particularly physics, and then the interesting piece is the boundary conditions. Let's take a look at those. So what I'm saying is, at the bottom here and at the stage outlets, right, I want to define my outlets. So here I'm bringing air out of the occupant zone, right, under each of these seats. I could also now hide these things, but I don't want to go into detail here. Inlets, I'm bringing it in with a certain temperature, with a certain velocity. I'm bringing in the fresh air, the conditioned air, right? And then the rest is actually pretty much straightforward. So I'm saying, okay, I'm going to treat my walls as adiabatic. I have my occupants generating heat, right? So all of them are defined as heat, as a heat flux. And then the adiabatic, the last one, right? So it's as simple as that. So we're really looking at a very simple setup to set up. And the next step is then simply computing it, right? And the computation of it is something that in that case is quite significant, because let's take a look on how many cores I ran this one. Quickly bringing the application back. So here we can see that I ran this simulation on 96 cores, right? So I really wanted to make sure that I'm taking advantage of all the cloud computing power of SimScale, and I'm running that on a large machine. So the entire problem here will be split up in many, many small cells that I can see here, right? And this cell count, so the number of these mesh cells that I'm seeing here, is really what makes my problem or my simulation time-consuming, computationally intense. And so on a local machine, on a local computer, you couldn't run this simulation anymore, right? On a normal, I don't know, 4-core machine or 8-core machine, it wouldn't be possible, right? But thanks to the cloud, I can run this big mesh simply on close to 100 cores, and that's what I've done. And then afterwards, visualize the results, and that's what we're going to take a look at now. Let's go back to the presentation. Take a look. Again, this is what we've specified, right? You've seen a top inlets, and we brought the used air out at the bottom, some heat sources, and some stage outlets. And on the right, we can see the velocity field, right? A visualization of the velocity field. Let's dive into more details. Here we can see 3 slices through the air domain and how the velocity on these slices looks like. So I could see what I would expect, right? I'm bringing it in from the top, so I have quite high velocity directly under my inlets. And I can immediately see, oh my gosh, right, this is not well diffused, right? So here, okay, that's not a good piece. So I could bring in some diffusers or something, but it's immediate thing I can see, right? The whole thing is poorly distributed, right? I have very high velocities here, but down here I almost have no velocities anymore. So it looks like, yeah, that already raises some eyebrows. Temperature, same thing here. So I'm bringing in cool air from the top, but then it's not well distributed. So it's very cold over here. So I'm at 22 degrees Celsius here, but the people to the left and right of the inlets are at rather something like 25 to 26 degrees Celsius. So that doesn't look good. And now what we're here for, right? We want to make sure that our design meets the standard we're designing for. And I can see already right here, right now, oh, that's going to be tough, right? Remember, what we want is our PMV, our predicted mean value, predicted mean load, to be between minus 0.5 and 0.5, right? And everything blue means it goes too cool, slightly too cool is the official definition, right? And everything above 0.5 would go into the direction of slightly too hot. I mean, the good news is that I'm not anywhere below -1, and not anywhere above or significantly above plus 1.0. The bad news is, let me draw something here. I mean, these guys will feel cold, right? Those guys. That doesn't look good, right? These people here are not well ventilated. These guys might feel too hot. These guys might feel too hot. So this doesn't look great, right? I mean, this is something we can do better. Let's take a look at PPD. Same here, right? Let's quickly remember, we want to be everything either white or green, but nothing to be red, right? And I can immediately see that a significant portion of the occupants sit in a red area. So that's not good. And here also we shed some light on PPD versus PMV. So PPD doesn't give you a hint whether or not something is too hot or too cold, right? This guy doesn't feel good, and those guys don't feel good, but for different reasons, right? PPD just shows us that they don't feel good. All right. So let's take these learnings and quickly iterate, right? And that's literally what this is about, right? We're using the ability to predict virtually how our HVAC system will perform and whether or not it's going to be compliant with the specific code we're designing for. And we use these learnings to simply change the design, right? And again, we're looking at a scenario here today, right? We could have done many things. We could have diffused the air better. We could have chosen, I don't know, a displacement ventilation strategy, you name it, right? We see our customers coming up with all sorts of great design ideas and great approaches. So our customers know better how to do that. But what we want to show is how you can then test a new design iteration quickly, right? So as simple as that, we simply bring the mixing ventilation outlet, so where we bring in the fresh air to the top, and we bring in we bring out the used air here, and we bring in the fresh air below the seats. So we turn the mixing ventilation system around. We still bring it in quite significantly fast. So we could even say it's a displacement strategy, but I wouldn't go that far. We're still mixing significantly because we're bringing in at a lot of areas. The rest is unchanged, right? Same simulation setup, same heat sources, and except for the changed outlets, all other inlets and outlets are the same. And we run it again. And here on the right, you can see again the velocity field, and that already looks like something that we like more, right? Let's dig deeper. We can immediately see that we've reduced the areas in which we have very high velocity north of 0.3 meters per second significantly, right? It almost looks like we do not have any occupant zone anymore where we do have ventilation, where we do have velocities north of 0.3 meters per second, which is what we like, right? Temperature-wise, we're seeing that at the top, we're certainly getting hotter, but it looks like most of the occupants are actually now not in the danger of overheating, right, or of being at a temperature where it's simply too hot. Now, what we're here for, let's take a look at PMV, and that's a view we like, right? We can see that nearly, or actually all our occupants are in a green region, right? So above minus 0.5 and below 0.5. I mean, here it's getting close. Let's take a look, right? I mean, here it's getting close because this is, again, where we have the outlets where most of the used and already warmed air is streaming out. But still, looks like we're good PMV-wise. And then the same goes for PPD, right? Most of our folks sit in a green area and a few of them in a white area, which is still fine, right? And we can see that we're overall, across the entire occupant region, we're at 5% PPD. And we are compliant with EN 15251, right? And that's ultimately what it comes down to, what we wanted to achieve, right? And the beauty of this is that we've done it just based on our drawings, right? We digitally designed this. We quickly thought about what's the operating point of our HVAC system, and let's make sure that based on this operating point, based on the energy efficiency of this operating point, I can achieve a certain thermal comfort. And then last piece to this, to make sure that the power of this got clear, we didn't use at all any different energy, right? We used the exact amount of conditioned air. It was the exact amount of energy we put into the system, but with a significantly better outcome, right? Now, quickly comparing them, I mean, this is very obvious, right? On the right, we can see design 2. On the left, we can see design 1. We can see again that it's much better, that we have a much better airflow through the occupant zone. Same in this here, right? We got rid of these big vortices generated directly at the inlets, so that looks great. Same with the temperature, right? In the direct comparison, I can see that it's a smoother temperature distribution and that I have less of my folks sitting in high temperature areas. This looks good. And then also here, right, much better, a much better sort of distribution of airflow across the audience. And then PMV, what we're here for, right? Again, everything green, and on the left I can see that multiple of these folks are sitting in an area of PMV, both above 0.5, but also some below minus 0.5, right? And all of these people will be dissatisfied, and it's not good for my code compliance. Same goes here in a side view. And then PPD, last but not least, PPD in direct comparison. Again, clear picture, right? Just to remind again, this is the same energy put into this system. It's the same amount of conditioned air we brought in here. All right, wrapping all of this up. In a nutshell, what we've done is we quickly ran 2 simulations, right? So we had 2 designs. All of this, you've seen it, right? The physics to set up is easy. The mesh generation is highly automatic. The simulation is highly automatic. So we basically just invested computing time, right, which is cheap. And we saved on manual time. We had everything ran in the cloud, so there was nothing, our computer locally wasn't blocked. Everything was just handled. The heavy lifting was done in the cloud. And the return on this investment is that if I would have moved forward with my first design at this operating point that I was foreseeing of my HVAC system, 15 occupants would have been uncomfortable, right? I would have had a PMV or I would have had a PPD north of 10%, and I would not have been compliant with the standard I was designing for. And afterwards, we are, right? And we have the confidence to move forward with this design. And this is what it comes down to, what we're seeing many customers succeed with CFD and SimScale. If that got your attention, there's 2 things you can do. The first thing is, if you do not have yet a SimScale account, just go to simscale.com and create one. It's going to take you 2 minutes, and you can see that for yourself. If you have already an account and you want to dig deeper into this project, this particular project I showed today is available as a public project under simscale.com/projects. Just search for, I think you should find it under theater, and you'll be able to dig into the details of this setup and see for yourself, in more depth how it was technically set up. Great. Unfortunately, it took me 10 minutes longer to deliver that session today. I hope you still got value out of it. Since we're running so much over time, I will cut short in the questions, but I'll address them afterwards individually for the people that send questions, so thanks a lot. And with that, I'll wrap up this today. Again, thank you so much for your attention today, and I hope to see you on the SimScale platform soon. Take care and goodbye.